Hello everyone. This is a new series that we are starting on binary search. And let me tell you, binary search is one of the most important and quite frequently asked topic in algorithmic interviews. Like the problems related to binary search appear very frequently, but it is a quite intuitive topic. And the main goal of the series is how to recognize binary search and how to prove if binary search can be applied in a problem. Although I will be using Java to code up the solutions, but this entire series will be language agnostics. We will be mainly focusing on how to recognize and how to apply binary search. And just to make thing look real, I will be recording entire video of this series in one cut, right? So let's get started. So first of all, before moving to binary search, we need to understand this concept of search space. So what is a search space? Search space is the space in which your answer lies. So for example, if you are searching any element in an array, then your search space is from index 0 to index n minus 1, where n is the length of the array. Because these are the potential answers where your element can lie. Similarly, another common example is, let's say you have to return the length of the array, then you can return anything from 1 to n, right? The smallest subarray length is 1 and the biggest subarray's length is n, where n is the length of the array, right? So these are some common example of the search spaces. Now, since binary search is one of the searching algorithms, the other very common searching algorithms are linear search, depth first search, breadth first search, and so on, right? So now, moving ahead, let's take some problem and we will try to understand this space using some example. Let's say you have some problem, and right now the problem is not important since we are learning about search space. Let's say you have some problem in which the answer you know lies in the range of 1 to 100, which means you know the result that you will have is from 1 to 100. Now, one way to solve this problem is you can definitely go to each of the possible candidates, which in this case would be 1, then 2, then 3, and moving on so forth up till 100. And then you can check each of the candidate if that can be an answer, right? Now, since you are checking each candidate, right? So the type of search that you are doing in this case is linear search, right? Now, how does binary search differs from linear search? Let's say you had some search space 1 to 100. Now, if at any point of the search, for example, you were at, let's say, 50. Now, at some point, if you can for sure say that your answer will lie either to the right or to the left, which indirectly means you can completely ignore one part of the search. Like in this, we have divided the search into two halves. If you can for sure completely ignore one of the halves, like completely ignore searching in one of the halves, then we say our search space is monotonic. Like the technical jargon here is monotonic. And whenever the search space is monotonic, we can apply binary search over there, right? So this is the very first thing which you should keep in mind. If you can prove that your search space is monotonic, then for sure you can apply binary search. As we have discussed over here, if you are at some candidate and depending upon that you can for sure say that your answer will lie either to the left or to the right, then in that case you can definitely say your search space is monotonic and binary search can be used over there, right? Now let's directly move to some problem. The very first problem and the most fundamental problem here is, let's say you are given some array. You are given some array which comprises of only 0 and 1, and the array is sorted in non-decreasing order, which means first of all it has all the zeros, then it has all the ones. So this could be one potential array which follows this property. Now the problem that we are discussing over here is the most fundamental problem on binary search, and this problem is very important. We will see that in a few moments, right? Now in this, like, regarding this array, the problem that needs to be solved on this array is find the index of first one or last zero. So this is the problem, and we need to figure out, rather not or, we need to figure out both the indexes. We need to figure out what is the index of first one, which in this case would be, if I start my indexing, 0. So the indexing over here is this thing. And regarding first one is present at index 5. So we should return index 5 over here. And last 0 is present at index 4. So we should output index 4 for this problem, right? We have to solve both of these problems individually. So let's try to focus on any one of them, and then we can approach the other problem using the similar way, right? So let's copy this array. So first of all, we have 5 zeros, right? And then we have 4 ones, right? So here again, we are interested in finding the first one. So the problem we are solving over here is find the first one. Then we will move to the problem finding the last zero, right? So first of all, the very obvious thing that we can do here is, since this is an array, so we can linearly scan all the indexes, right, from left to right. And whenever we encounter one for the very first time, we can directly stop our loop, break out, and just print whatever we got over here, right? So this is again a type of linear search which will do big O of n operations, right? But we haven't utilized the fact that the array is sorted. So let's try to think in that direction. And I have already told you, if we can prove that our search space is monotonic, which means depending upon some candidate, if you can for sure say that your answer either lies to the left or to the right, which indirectly means that you can directly ignore one half of the search, then for sure we can say our search space is monotonic, and we can definitely apply binary search over the search space, right? So if you see this thing, right, then initially I have to search in the whole array, right? So my search space is from index 0 to index n minus 1, where n is the length of the array, which in this case I think is 9, right? Now let's say you are at some index, let's say this is the fourth index. Now you know at 4 index 0 is present. Now we know at fourth index 0 is present. What does this mean? This means everything to the right of this, which means everything to the right of 4, which means index 3, 2, 1 and 0. It means all the values are 0. Why? Because we know according to the structure of the array, we have first all zeros, then we have all ones. Now for sure I can say my 1 will never lie to the left of 4. Thus I can clearly ignore this half, which means I need not to search anything in this half. I only need to search from index 5. Now, why index 5 and not 4? Because at index 4, 0 is present. So, definitely we need to search it in the right. So, now what I told over here, if you can prove that your search space is monotonic, which means that you at some interval, at some candidate, at some answer, you can for sure say your you can completely ignore some half, either it could be left half or right half depending upon what you want. Then we can say the space is monotonic and we can apply binary search. And we have seen in this problem, if I am at some index which has a value 0, then there is no point searching in the left, because I know according to the structure of my array, everything to the left of 0 will be 0, and I only need to go in the right because there only I can find a 1. This was for some index which has a value 0. Now let's say we have some index which has a value 1. Let's take this sixth index, right? Now sixth index has value 1. Now since this sixth index has value 1, so we know everything to the right, everything to the right of 6, which means index 7, 8 and so on, will have value 1. Now why 1? Because this is the array that we are provided. We will have first all zeros, then followed by all ones. So I can for sure say I cannot find my first one to the right of 6, because I know for a fact, since I am interested in finding the first one, so I know answer cannot be greater than 6, because I know at 6 I have 1. So I can completely ignore the right part and I only need to search in the left half. Thus, for both type of indexes, by both type I mean the index where 0 is present or the index where 1 is present, my search space is monotonic. Thus, I can apply binary search over here, right? So now let us see the very obvious implementation of binary search, which you might have seen in very other videos or discussion forums, which will be, this is like the snippet which we'll be using in most of the binary search problems, right? And we'll also understand what is the meaning of this binary search pointers, right? The low and high pointers specifically. So the snippet goes something like, while low less than equal to high, right? Then you figure out the mid, and then you check on some condition, and here you update one of the two pointers, else you update the other pointer. This is the standard implementation of binary search, the standard template that we will be following. You might have seen this earlier as well, but first of all, let us try to understand this template. First of all, there are some variables low and high, right? So let us briefly discuss about them. So low is the variable which points to the starting point of the search space. Similarly, high points to the ending point of the search space. Now, with regard to this example, initially you will start with low is equal to 0, because you have to search in the entire array, and your high will be the last index, which will be 8. Now why 0 to 8? Because 1 can be present, like the first one can be present at any of these indexes. So this is the current search space for our binary search, right? Now, why mid and why not something else? Because mid helps us to efficiently divide the complete interval into, like for example, if you had this interval, right, and you figure out the mid, and we have discussed if if at mid you can for sure ignore some left or right half, then we say the space is monotonic. And why mid and why not something else? Because mid helps to efficiently divide the search space into two halves. Otherwise, if you had taken some other apart from mid, then in some cases you would end up with a search space which is more than half. So mid efficiently helps to divide the search space into two halves, right? Now, if some condition is met, we will now this will vary according to the problem. But again, the general idea is if some condition hits, then you update the low pointer or the high pointer, and else you update the other pointer. And you also have to adjust answer over somewhere, which again depends upon problem to problem, which we will see for this case as of now, right? So now we were interested in finding the first one. So let's first of all try to understand how the binary search will proceed. We will take a shorter example in this case. Right? So here we are interested in finding the first one, which is present at index 4, right? So definitely one way I have discussed is we can go over all the indexes, but that is not the agenda over here. Now we have proved that we can apply binary search over here because our search space is monotonic over both 0 and 1. So let's start. So initially your low will be 0 and your high will be 5 because we have to search in the entire array. And how we have defined low and high? Low points to the starting point of the search space, which is index 0, and high points to the ending point of the search space, right? So we have low as 0 and high as 5. Now let's figure out the mid. If you figure out the mid, you will get mid as 2 because 5 by 2 is like the programming language will do a floor operation and you will get 5 by 2 as 2. So now we are at index 2. Now the value at index 2 is 0, right? Since the value is 0, so we know there is no point in searching to the left because we know all the values will be 0. We only need to go to the right. Now, when we need to go to the right, it means we are decreasing our search space. Essentially, we were first searching in the entire array, right? Now we only need to search in this half. Why in this half? Because initially our mid was at 2 and we figured out there is no point in searching up till index 2 because every value is 0. So we now need to search to the right of 2. So here you will update your low. As you can see, the starting point of the search space is now 3. So you can update your low as mid plus 1, which will now become 3. Right? You can see as well, the starting point of a search space is 3. And high will remain same, which is 5. Okay. So now let's again figure out the mid. If we figure out the mid, 3 plus 5 by 2, which will give you 4. Now we are at 4. Now we know the value present at index 4 is 1, which means searching to the right is useless because we are interested in finding the first one. But for now we know at index 4, 1 is present. So you need to update your answer as 1. Let's say you have some variable result. You updated it to be 4. Now why it needs to be updated over here, we'll discuss that. But we now know there is no point going to the right because we know since everything to the right of 4 will be 1, and since we are interested in finding the first one, so we for sure now know 4 is the least value which we have seen. 4 like is the least index which we have seen where 1 is present. Now we will look for a better answer. Now what does better means? We will look for a smaller index because we are interested in finding the first one. So we will now search in the left half. which means I am decreasing the high pointer. Why high pointer? Because you can see the starting range is still index 3, and we have moved the high pointer from 5 to 3 because we are searching in the left half. So in this case, your low will be 3 and your high will also become 3. Now, if you figure out the mid, you will get mid as 3 plus 3 by 2, which will be nothing but 3. And since like we have 0, so again the left part is useless, go to the right. Now going to the right means increasing the low pointer because we are increasing the starting point. So your low will become now mid plus 1, which will be 4, and high will be 3. Now if you see this thing, right, if you see this thing, then low less than equal to high. Here now low has become greater than high, so your condition will terminate. Because technically this means your high pointer is somewhere over here and your low pointer is somewhere over here, which indirectly means you don't have any such space because your low pointer has exceeded high pointer, right? You don't even have a single element, right? So there is no point of continuing the search. And we got 4 as the result, which you can see is the correct answer. Now why we need to update the answer when we are at 1? Let's try to figure out this thing, right? So why we need to figure out, like why we need to update the answer. Let's say you had this kind of array. Now let's say your mid came somewhere over here, which is this index 0 1 2 3 4 5, right? Now we know there is no point going to the right because since we are interested in finding the first one, and for sure we know 5 is the very, like the very least index, which has the value 1. So we don't want to search for 6 7 because we are interested in finding the lowest index. But we also need to update our answer till this index. Now why we need to update it? Let's say you don't update this thing, right? Like what does updating first of all means? You updated your answer to be, let's say, this index 5. Now we now are interested in finding a better answer. Better in this case means a lower index, right? So we will search in the left half, which means decreasing the high pointer. Your high pointer will be over here. Now, why we need to update the answer over here is because this could be the very first time you are seeing one, which happened in this case, right? Because let's say your mid came somewhere over here, because your mid is a very, like, your in binary search covers every possible answer in the search space. So your mid can come at any particular index, right? Let's say your mid came somewhere over here, index 3, and you didn't update the answer. Like, first of all, how would you update the pointers? You will just ignore the right half completely and you will search in the left. Now, searching in the left, you won't find anyone. We can see clearly as well. So, if you hadn't updated your answer, right? So, in that case, you wouldn't find 3 in this range. So, your answer will get never updated and you will be left with what you initialized before proceeding towards binary search, right? Which we saw because our mid came directly at index 4 after like fixing low as 3 and high as 5. If we hadn't updated the answer right over here, then we have moved to 3 comma 3, which you can see in this case, and we wouldn't have find 1 in this range as well, right? So definitely we need to update answer as we are on this range, as we are on the segment comprising of ones, right? So yeah, that's pretty much it. And now let's try to code this thing out, right? So let's start. As I've said, I will be using Java, but this entire series is not dependent upon language. I have told you the main aim here is how to recognize binary search, how to prove that whether we can apply binary search. Okay, so class, just a basic template, and let's take some array. Right, and now we are interested in finding the first one, and the answer here should be what? Index 3, right? Now, first of all, although I haven't discussed about the edge cases, but you can, let's say if the first value is 1, then you can just simply uh, not return, or maybe we will just create some function that would be a better way to implement. Let's say this is your array, right? And we are interested in finding the first one. Now, first of all, let us kick out the very obvious cases. If the first value is 1, which means array doesn't have any zeros, so your array will look something like 1, 1, 1, 1, right? So you don't have any zeros, so definitely here you can return index 0. Now, what is the other case? The other case is when all zeros are present, right? Which will go till the very end. So you can just check the end index, and if the end index has a value 0, then you can return a -1, indicating that no one is present, right? So here you can just simply return 0. Else, if a of n minus 1 is equal to 0, then you can return 1, return -1 in fact. So now let's start with binary search. Now we have to initialize low and high. I have discussed this multiple times. Low points to the starting point of the search space, which is index 0, because we are starting with the search and we don't know where our index is present. And high points to the ending point of the search space, which will be the last index n minus 1, because we have to cover the entire array initially, right? So your low will be 0 and high will be n minus 1. And let's say take some variable, right? Now we have to figure out the mid. Let's figure out the mid, right? Now, depending upon this mid index, like depending upon the value at this mid index, we need to update our pointers. So if the value at mid index is equal to 1, which means we are in the segment comprising of ones. So first of all, we need to update our answer. And since we are in the segment comprising of ones, right? So going to the right is useless because we want to find the first one. So we will look for a better answer in the left half. And similarly, if we are in the segment comprising of zeros, then going in the left half is useless because we know we will encounter all zeros. So we can only go to the right half, right? So if the value at the mid index is 1, so you now search in the left half. Otherwise, the value will be 0. So you need to search in the right half. In the end, the answer will be stored in the res variable. So you can just simply return result. And now let's try to pass some array in this function and see if this works correctly, right? So let's say this is the array that you have, and ideally it should return index 2 because index 2 is the very first time when you encounter 1. So let's try to print answer and see if this works. Yeah, this works correctly. Let me change some values. Let's say now ideally we should get 3, and we got 3, right? If I remove this 0 as well, then we got 4, which is absolutely correct. So we have solved this problem, right? Now, similarly, we started with two problems, find the first one and the last 0. We have done this one. Now we need to do the other one as well. And then we will discuss a brief about time complexity as well, right? So let's start. Now we are interested in finding the last 0. And how our array looks like? Our array looks like all zeros followed by all ones, right? So for this array, since this is the last position of 0, so you need to return 3 over here, because 3 is the last time you are seeing 0. Now again, very obvious way is you can scan through the entire array, and when you just encounter 1, you can just directly return index minus 1. Also in that approach, you need to ensure 1 is not present, like you have a single 0 at least, right? But that will again do some big of n operations, and we haven't utilized the fact that the array is sorted. Now this is again a very similar problem. We just need to understand one thing, and if we understand that, this problem can be solved very easily, right? So again, to first, how to prove binary search. Let's say you are at some index, right? Let's take this array again. Now let's say you are at some index which has a value 1, right? Now definitely, if you are at some index which has a value 1, so you can completely ignore the right half, because first of all, we are interested in finding the zeros, and we know that if we have seen 1, then we are in the segment comprising of ones, and everything to the right will be ones. So definitely we need to go in the left half, right? And when we are at some index which has value 0, then for sure there is no point in going to the left, because we are interested in finding the last 0. And for sure we know 2 is the least index, like 2 is the largest index where we have seen the value 0. So we now need to search for a better index. In this case, the better means a larger index, whereas in the previous case, the better mean the smaller index, because we, in this problem, we were interested in finding the first one, right? So if we are at some 0, then we need to go in the right half. So both of these points are monotonic, because at both points we are able to clearly reject one half of the search, right? So we can say we can apply binary search over here. Now again, you have to update the answer when you see a 0, because this could be the very last time you are seeing 0. For example, let's say you came at some index 3, right? Now you know your answer will lie to the right, because we are searching for a better index, which means a larger index. So your search space will be now from index 4 to the last index. But now you are in the segment of all ones, so you will not find a 0. So you need to update your answer whenever you see a 0, right? So almost same code, and how we can do that? Let's see. Just we need to adjust these two things mainly, and we also need to handle the edge cases. So one of the edge cases is 0 isn't present, which means your array should start with 1, which means in this case you need to return -1, indicating you don't have any 0. And if the last value is 0, then you can simply return 0, because then you have only zeros, right? And now again, starting with low and high, which will first initially cover the entire subspace, right? And if a of mid is 0, right, which means you are in the segment comprising of 0, so you will update your answer, because this could be the very last time you are seeing a 0. And instead of like going in the left half, we now need to go in the right half, because we are looking for a larger index. And whenever we have seen 1, which means you are in this segment, so going in the right is useless, search in the left, right, because we are interested in the last 0. So here we will have high is equal to mid -1, right? Almost same code, we just have inverted the conditions depending upon what we were searching. Now let's try to run this thing and see if this thing works. And according to this case, we should get index 0, 1, 2, 3, right? So let's get started. We got 3. Let's look at some other case as well. Let's pass this array. Here we should get 2, and we have got 2, so this works correctly. Now before wrapping up, there's still one thing which needs to be covered. So first of all, let us briefly prove the time complexity of binary search. Now, initially you started with, let's say, n elements, right? Now, at every search, right? At every search, you are updating your pointers, right? Depending upon the condition, right? If you see, after figuring out the mid, right, and checking the value at that index, you are updating your low and high pointers, and we have seen our search space is getting halved each time, which means if you started with n elements, then your search space got divided into two, which means n by 2, right? And this n by 2 also then got divided into half, which means n by 4, right? So let's say you did some you did this space you did this search for k times, which means these are this will actually tend to 1, because we will stop our binary search when we are at a single element, right? So if you just, and in this case, k is the number of times our search has executed, which means this is the condition, right? Now you can take 2 power k to the this side, which will get converted to 2 power k, right? And here, if you do some maths and take log, you will get k is equal to log of n to the base 2, right? So now this is very efficient than a linear search. How? If you do a linear search on, let's say, an array consisting of 10 lakh elements, right? So you will do 10 lakh operations, but if you do some kind of binary search, then it will take only 20 operations. You can see how much binary search is efficient and scalable, right? So that's pretty much it from the time complexity part. Here n is the search space, which in this problem is the length of the array, right? Because index 0 to index n minus 1, right? Now, guys, one important thing over here is every binary search problem can be modeled down to this problem. Either finding the last zero or finding the first one. Every binary search problem can be modeled down to this problem, which we have discussed in this video. You just have to spend some time, first of all, proving that whether we can apply binary search. And I have, like, although this will come with practice, but we will see how we can use some different tactics to think that our search space is monotonic, right? So where were we? Yeah. So I have told you we can convert every problem of binary search to this problem, provided that we can apply binary search, and the problem will boil down to either finding the first one or the last zero. We will see this how to model in some future problems which we will do. But for this thing, you should keep in mind, if you are able to convert every problem to this zeros and ones, then definitely your life will become very easy with this hack, right? So that's pretty much it. We will continue with the next video. Thank you.